Hi all, Celso Batalha, Evergreen Valley College, Astro 10 Online, and I would like to go over some of the main topics. Chapter 4, this is the chapter we are focusing this week, and I would say is perhaps the most important chapter of them all. And let me recall observations I made in the first video that usually when we think about astronomy, we think about going out and identify sky objects like constellations and Big Dipper, things like that. So this is cool, but this is not what we do in astronomy. So astronomy is a science-based um, knowledge or curriculum, and as such is pretty much dependent on the scientific method. And then one of the things we saw with respect to the scientific method was nature is the one that initiates the process and is the one that ends the process, in the sense that you observe nature behavior in such a way and you observe some regularity or some phenomena and you want to explain that. And then you come up with your hypothesis and and then you test your hypothesis. And again, the hypotheses have to be made of arguments that can be tested. So you cannot invent anything you want to explain what happened if you cannot summon the elements of your hypothesis into a lab and test them. So that's very important. So I cannot say that um, the cup. I have a cup in front of me here, cup of coffee. I cannot say the cup will never leave the table, or I could say, well, if I wait enough, this cup is going to be lifted by the soul of my grandfather, right? If I just stay staring for a long time, I cannot use this as an argument. First of all, I mean, I never saw this cup kind of a lifting without somebody holding. And also, I one of the elements in my arguments, the soul of my grandfather, I cannot bring that to a laboratory and measure and do things like that. That was never done. So it's not a valid scientific element to put in a hypothesis. It doesn't mean that you shouldn't believe on that. It means that as far as in the scientific realm, I cannot use that. Now, um, in the first day, I mentioned that. So you initiate with your hypothesis, and then you test your hypothesis, you create a theory. But nature is the last word on everything, because as technology advances, perhaps we might develop such instrumentation that will reveal aspects of nature we didn't know when we formulated our theory. And then the theory has to be redesigned if it cannot explain these new aspects of nature. So nature is always there. So we use nature as a checkpoint. Okay, how can we do science with astronomy? Have you ever brought a piece of a quasar to the laboratory, sir? You could ask me. Have you ever brought Andromeda Galaxy to your laboratory, sir? Yeah. Have you gone to, let's say, Proxima Centauri, which is the closest star to us? Have you gone there and realized it is made of the same kind of stuff we have here on Earth? Hydrogen, helium, calcium, carbon, so on, so on, so on. No, have not. And then you could say, hey, how come you say and you mention that astronomy is scientific? So you have a bunch of theories, you cannot test them. That's why this chapter is so important. It is important because although we haven't gone to these places, light that is produced in these places or has interact with the material in these places has gone to us, has come to us, in fact. And we collect this light, and we analyze this light, and we read the signatures on this light that can reveal the state of matter, the state of affairs, if you want to use that expression, in the environment the light was produced or interacted with. So that's the main point. So astronomy is based on light and the instruments used to collect this light. And yes, a lot of physics. So the physics we use to explain what is going on out there is the same physics that's used to create your cell phone, and you use and you love it, right? So the physics is the same. The relativity that is in there is the same. The physics that is used to send out communications from here to Europe is basically the same. The understanding and the knowledge we have of all the factors involved in producing knowledge here on Earth and in our laboratories is the same, used to apply to these faraway objects. And why? Because we know how light interacts with matter. We don't have in our course a lab counterpart, but the Astro 10L has several exercises that you can confirm all the material, all the evidence we have in this lecture course. So, and in particular, I'm talking about photometry and photometry and spectroscopy. So photometry and spectroscopy are the two main tools astronomers use in order to unveil what's going on out there. And those are primarily based on how we know light behaves. So let's see what this chapter presents to us. Here's a schematic of a telescope. Aperture is the diameter, the size of the main optical component of that telescope. Could be a lens, could be a mirror. Eyepiece, for amateurs, is very important because it's what allows you to see things. Professional astronomers don't care for eyepiece because they wanted that information, the image or whatever is being collected. They wanted that to go to their computers so they can analyze directly. Secondary mirror is a device that is used to diverge light from the primary mirror, which you see in the lower right-hand side, and send that to some places. So this chapter introduce you to what light is, the characteristics of light as wavelength, frequency, and the speed of light, which is a constant value, and what telescopes are and what type of technology exists in association with telescopes, optical telescopes, ultraviolet telescopes, radio telescopes, so on, so on, so on. So basically, I mean, how do we know light has a finite speed? So light, as we know today, has a finite speed, and in 1600 that was found by Ole Romer, and he used the timing in which Jupiter in the 1600s, the timing in which Jupiter moons would go in and out of eclipse. And so, for instance, some of these moons might take 40 or so hours in order to come in and out of eclipse, which means you cannot observe that in few hours during nighttime. Sometimes you have to observe several, the beginning of an eclipse in a cycle, and observe the final moment in which the moon comes out of eclipse several rounds after, because that's when you can observe. And when this happens, Earth might not be the same position in the sky, neither Jupiter, which is based on the moon's, the eclipse of the moon's, this measurement was made. But Ole Romer was able to determine that there was some delay in the arrival of the final completion of this eclipse, and he speculated this mismatch was caused by the fact that Earth was further away from Jupiter as it was when the eclipse started. And by determining how far Earth was from the beginning of eclipse, he could then speculate this delay was caused by the fact light has a finite speed. And then by knowing the distance and the time of delay, he could then infer the speed of light with relatively good precision, based on the instruments and the technology he had available in those days. And by the way, he died, and his predictions were not confirmed. People didn't believe on that while he was alive. So only after his death is when this the result of his research was embraced by the scientific community in those days. This is pretty much 1600 we are talking about. So, but as we understand light today, light has two aspects. The main aspect of light, and that is the classical one, light is a wave. And why do we say light behave like a wave? Well, because we can go to the laboratory and we can do experiments that prove light behaving like any other good waves. It has refraction, it has interference patterns, it has distractions and constructive maxima and minima, and you can make predictions quite well. You take the instruments and you take the students, and then you say, hey, this is behavior of a wave. And wave, there is a good example here in the part A of a faucet that is dropping water, and then you have this circular wavelength coming away from that. So you could see light as a wave, and as a wave it has a wavelength, which is the distance between trough or the trough points or the maxima point in a wave. So that is the wavelength. Amplitude is the distance between the resting part of the wave and the toppest point. And the speed is given by the speed of a wave is given by the speed in which propagation of this energy takes place. And we learn from physics there is a relation between the speed, frequency, and wavelength. And see if I don't think I have an equation here, but in our face-to-face, I will be able to write things down and talk to you about it. But basically, the speed of light is equal the wavelength times the frequency. Or in other words, you can say that the wavelength is equal to the speed of the light divided by the frequency. And which means, so if the separation between these waves is inversely proportional to the frequency, so when the wavelength is pretty high, when you have a high wavelength, yes, yeah, no, it can go. Yeah, sorry, I was distracted here. So, so when you have as I was saying, the wavelength is given by the ratio between the speed of the light by the frequency. So when you have large wavelength, when this separation between crests is large, it means you're talking about a small number in the frequency. So the frequency is short, is small. By the same token, if the frequency is high, then the wavelength is small because the frequency goes in the denominator. So bigger number in the denominator implies the ratio, which is the wavelength, is short. So short wavelength is associated with the high frequency type of radiation. So here you have the questions. Question A, as the frequency increases, the wavelength decreases. This looks good. So for high frequency, the wavelength is small. As the frequency increases, the wavelength increases. No, because they are not directly proportional. Changing the frequency has no effect on wavelength. Of course it does. Okay. So in the case of optical light, you have a picture of a rainbow here, you have the different colors. When you separate the white light, so as a wave, you see these different colorations which indicate different frequencies. So again, the red frequency and the bluish frequency, which is more to the left, they have different values. So the red frequency is one that is shorter than it is in the blue range. So which means the wavelength associated with the red color type of electromagnetic radiation, the wavelength is bigger than it is with the wavelength associated with the violet part of the spectrum. Okay, so violet is the shortest wavelength possible. So, and again, if you go to the lab, you can play around with all these different experimentations, and you can go to more specialized experiments with diffractions and things like that, which testify that wave for this type of instrumentations we have in the laboratory really behave like a wave. But voila, in the 1900, early 1900, it was also found that light can behave like particle, like a little bundle of energy packed together like a particle. The name of this particle is photon, P-H-O-T-O-N, photon. Photons. So photons are particle of light. They all have specific frequency, which means they have associated with them specific wavelengths, and the energy of these photons are directly proportional to the frequency they have, right? So high frequency photons are associated with very energetic type of radiation. Like when you go to the doctor and the doctor takes an x-rays of your body, I mean, the doctor, she hides herself, behind all kind of shields, because the energy associated with X-rays are much larger than the energy associated with the optical radiation, with the visible light. Both of them are electromagnetic radiation, but the visible light is less energetic, has less power of penetration, and X-rays just go through and might damage cells if the exposure is too severe. So that's a good example. Another one, gamma rays, is another aspect of electromagnetic radiation. It's very energetic. It is abundant in processes associated with star collisions. So we've got to have a lot of energy associated with that, or start exploding in supernovae, as we are going to learn in a few weeks from now. But you don't find it abundantly here on Earth, except in some decays that occur in atoms, but not enough to give us some major damage. So gamma photons as particles. So, and then you stop and think, hey, well, what are you talking about? You're talking about that something that we call electromagnetic radiation behaves like wave and behave like particles. The answer to this question is no. It depends on which instrument you're using to detect that reality, if that makes sense. Some people might argue against what I'm saying because I'm saying there is some reality, right? And I'm trying to measure that reality. Some physicists might say, hey, what you really have is instruments of detection, and depend on which instruments you are really using, you can detect that thing as a wave thing or as a particle thing. Um, so here is the whole electromagnetic radiation, the energetic ones in the left-hand side, gamma rays, X-rays, ultraviolet. See this little tiny rainbow in there? That is the visible light. See the wavelength associated with it. It's just a small fraction, and we miss the entire infrared, microwave, and radio waves. All those frequencies we are not so much, at least aware here on Earth. I mean, of course, we are surrounded by all kind of radio waves, but we don't see it. Our eyes are capable of detecting only the optical light. And because we have these natural detectors pretty much built by Mother Nature in response to the sun, which is the star putting most of its radiation right at that band, and because of that, living organisms that happen to we happen to be part of it, developed detectors that allow us to move and migrate and browse through this environment that is bathed on this type of radiation. But if we had a different star, kind of a bluish one or more ultraviolet, and if life developed around this star, probably life would develop mechanism of detection that would enable them to survive in that type of environment. That's just a speculation, basically. I don't know if there are life out there, although certainly I think there is. Why not? But I mean, we don't know. But we might know, in a few decades or so. And spectrographs are instruments that what they do, they take the light and open up in a rainbow and it's spread out. And by doing so, you can analyze in detail aspects of interaction between light and matter. And in chapter 10 or 11, if I'm not mistaken, we are going to deepen this understanding as we explore transitions of atoms that are responsible for putting lots of these fingerprints in electromagnetic radiation. Of course, our eyes are a nice detector. So the light comes through the lens. There are the ciliary lens, there are the aqueous liquid that help to refract light even further, but all this light is shoot in the retina, and that information is read out somehow and sent through the brain to the brain through the optic nerve. So if you have a problem in an optic nerve, even if you have very good, eyes and lens, you might not be able to see it. So optical neuritis is one of these inflammations in the optical nerves that cut that communication and you stop seeing. I mean, although the eyes seems to be very good. Okay. Okay, so we are talking about eyes, but are there eyes or detectors in astronomy? Yes. And I don't know if you have a cell phone. Do you have a cell phone? Yeah. Okay, everybody has a cell phone nowadays. But cell phones, they have nice cameras, and these cameras use CCD charged couple devices. You see one of them, or an array of one there. And what they do, they take the light and convert the photons. Now light is behaving like a particle. It converts these photons into electric charge, and these charges are accumulated in components named capacitors, and then they are read out every time or so. And when they are read out, then you have an image, or you have a spectrograph, or you have a spectrum or something else of that particular object. So detectors are nowadays as important as the telescope are. So telescopes have this ability of collecting light. Detectors have the ability of taking the light and store them and transfer them to computers where astronomers can work on. Telescopes. There are two types of telescope: reflectors that use mirrors and refractors that use lenses. So there are two different components. If you go to our observatory, you're going to see them all. We have both refractors. Um, in the dome building is a refractor. And we have reflectors that use mirrors. Most of the portable telescopes we have are reflectors. Refractors bend the light, as you can see in the lower uh, display, C. And in B2, it shows refraction going on when the light change its original direction. So what are the main parts of a telescope? The main optical component that can be a lens or can be a mirror. The focal length is the distance between the optical component and the point where the image is being formed. That's the focal length. And so if you are talking about a refractor like the one in this figure here, have a big lens there called objective lens right at the entrance of the telescope. On the left hand side, if you look both telescopes, one is short, has a small focal length, the other is long, has a bigger or larger focal length. So these two telescopes are designed in such a way, just for um, comparison, in which the smaller telescope has a fatter lens, right? It's more open than the other one down below in figure B, and the images are different too. So the image of the telescope A is smaller than the image of the telescope B. So longer focal length have an image that is kind of bigger, which means you have to integrate, you have to collect more light in order to achieve some optimal image that has a good signal to noise, as we astronomers would say. Whereas this telescope of shorter focal length, the image is kind of a more compact. The light is concentrated onto a smaller area, so you don't need to integrate that much. So when you buy a telescope, especially if you are an amateur, you wanna buy a telescope that can be a good tool for the things you want to do. We can chat about it, and I can share my opinion on what type of telescope you should purchase if you are to start. My opinion is you shouldn't buy any telescope. You should associate it with organization like San Jose Astronomical Association. They have tons of telescopes and can lend it to you. You can learn a lot of what you like to do, and then when you know what you like to do, you can invest your good money in a good instrument that can do what you want to do. The idea of just buy a telescope just for fun, it's not a good one. It will end up in the garage full of dust. Not a good thing. And here is a telescope that has a mirror, has a primary and a secondary mirror, and the image is formed behind the mirror itself. You can see the focal plane indicated in there. So the atmosphere gives a lot of transmission in the atmosphere, depends on the wavelength. See the optical region, the one in rainbow against the black background. It's pretty much transparent. So that's why we are happy here, right? So the atmosphere and life on Earth kind of adapt to the energy the sun emits, and the atmosphere kind of open the windows and say, hey, we can see all of that. But it's pretty much opaque to a more energetic type of radiation, and is also there are good transmission in the radio band, but in some radio bands it's not. So we call those atmospheric windows, or windows where you can see things, right? So which means if you want to study gamma rays, if you want to study X-rays or certain frequencies in the ultraviolet radiation or infrared, you have to go up to space. You have to go beyond or above the atmosphere. You have to pretty much employ space technology. Um, and and there are aspects of telescopes. I don't want to go in that detail. We can do that in the chat room, which are resolution and magnifications, and so on, and so on, and so on. So, but basically, in this chapter, it introduces light and telescopes. Telescopes, they collect information, and light is the information. So yes, astronomy is scientific because we know how light behave, and we know how light interact with matter, and we know what sort of a fingerprints matter introduced on light, so that when we read and we interpret that, we can infer properties of these faraway objects. So then we know surface temperature of stars, we know what type of chemical composition they have, we know how fast they rotate, how uh, how fast they are going or moving, and we can even apply the same phenomena and the same knowledge to unveil characteristics of galaxies, clusters of galaxies, so on, so on, so on. They are so far away, you can never go there even in your wildest dream. Okay, have a good one.